Last day in class, we talked about energy to begin with. And then after that, we talked very specifically about electricity. What is electricity? What is electricity? Yeah, the flow of electrons. If electrons are moving through probably a wire, that's electricity. And the cool thing about electricity is that we can use it to do a lot of interesting things that like 100 years ago we didn't have. Right? Okay, I just was on my soapbox preaching to you guys about the world we live in changing. But like it has, hasn't it? Right? I mean, even talk to your grandparents about the world that they lived in. I mean, my grandfather just died a little while ago, and it was really cool because we got a chance to listen to a lot of stories about him and reminisce about his life in the 50s and 30s. And wow, that was a different world that they lived in. They didn't have microwaves, and they didn't have the internet. And like the world we live in now, almost everyone's got a cell phone, and everyone's got an internet. And my 1-year-old knows how to use an iPad, for crying out loud, right? Technology has fundamentally changed our lives, hasn't it? Right. Anyways, on my soapbox again, I'm preaching. Let's get back to the notes here. I want to tell you a little bit of history here. We have talked about this guy before, Rutherford. You guys remember Rutherford? What is he known for? What was the name of his experiment? It was called the gold foil experiment. Basically what he did is he shot a whole bunch of particles at a wall, like that. Only that's not what happened. They went right through, which like made no sense to him, because he thought that as he shot particles at a wall, they would bounce off of it, and they phased right through. And it fundamentally changed science forever, because rather than thinking that an atom was a ball, we actually know that the atom was a nucleus, and around the nucleus were electrons. And here's why that's important. It meant that electrons can move. Remember the previous model of the atom before Rutherford? It was Thomson. Thomson thought that there was like a positive bit, and inside of it were little raisins. You guys remember the idea of plum pudding? But like with Thomson's model of the atom, electrons were kind of like stuck inside of this thing here, right? But because we know that a nucleus exists now, and that all the matter is in one little nucleus, these electrons, they can move. And once scientists realized that electrons could move, they realized they could harness them and do something with them. Does that make sense? So that's what we want to begin our lesson with today, is the idea that we can form ions, where those electrons can become charged. Now, before Rutherford, scientists knew about charge. They actually experimented with it, but they had no idea what they were working with. They didn't know the theory behind it, but they knew that there were charges. For example, has anybody ever had this happen before, where you like scuff your feet against the floor and you get like a little zap? You ever had that where you get a little shock? I even get it when I get out of my car. I'm sitting in my car, I get out of the car, and I touch the door frame, and I get a little zap. Anyone ever had that happen before? You've probably experienced this at some point in life. That's static electricity. And really, they didn't know about static electricity. They didn't know how it was working, because they didn't know about these electrons yet. But they understood that you could zap somebody. Right? So the word I need you guys to know is static versus like flow. Electrical current, electricity, is always flowing in a constant loop, around in a circle, over and over and over again. But like static electricity is where you do like, try to zap somebody. That happens once. Right? That's like a static discharge. What is the largest type of static discharge that we know about? We even talked about it yesterday. Yeah, lightning. Lightning is a static discharge where static electricity builds up so much and then it finally goes zap. But is it a current in a circuit? No, because it just happens once. A circuit, it just keeps going for forever and ever and ever in a loop. So here's what I got for that picture right here, right? This is a good example of static electricity. A whole bunch of electrons are on the bottom side of a cloud. Who asked me about this yesterday? Yeah, good question, because it was in today's notes, eh? How does lightning occur? Well, the top of a cloud becomes positive and the bottom becomes negative. And then all of these negatives eventually form into lightning and zap themselves into the ground. Really cool, hey? So here's a principle that I need you guys to know. Maybe you already knew this, maybe you didn't. It's that things that are the same repel each other. Things that are different attract each other. And you might have already known this through, like, say, magnets. Anyone ever played with magnets before? And you, like, try to put one side of it together, and, like, they don't stick, right? But you flip the magnet around, and then all of a sudden they stick together, right? The same thing works with positives and negatives. If you have positive charges, they want to repel each other. And if you have negative charges, they want to repel each other. But if you have a positive and a negative, they want to attract. You ever heard this before? So the word we use then is either the word opposites, and almost everybody knows the word opposites, but you might not have heard this word before. We use the word like charges. Now, like has a lot of different meanings. My daughter in grade 1, she likes a boy. That's a little different than this. She's like, Daddy, I like a boy. And I'm like, oh, you're in grade 1. Anyways, she probably doesn't need you guys to know that. But, like, the word like in physics means something different. Like in physics means the same. Okay? So, like in physics means the same, not like, I have a crush on a boy, Daddy. She's 6. I know. Okay, anyways. Okay, I want to do a couple of demonstrations here to kind of illustrate how this works. So I'm going to move away from my PowerPoint for a bit. I want to show you a couple of demos here. I've got some of my Physics 30 equipment here. If you guys cannot see, can you come a little bit closer? Because this is kind of like close-up magic. So feel free, get out of your desk, come closer here. Close enough you guys can see. Well, it's not really magic. Okay, Alexa, you're going to be my assistant, I guess. This is magic, apparently. Can you just hold that? That's all I need you to do, just hold this. Okay, so I'm going to try to create some static electricity using this fur right here. Now, has anybody, I don't have one, but has anybody done the thing where you, like, rub a balloon against your hair and then stick it against a wall? Okay.
Like the plastic slide so everyone would go under it just to see their hair go up.
Okay, so I'm going to stay with me here. I'm going to do something similar. This is just a plastic rod, and I've got a fur. And it's very similar to the balloon on the head idea. What I'm going to do is I'm going to rub this thing right here. And you might even hear electrons moving. You have to be really quiet here, but see whether you can hear a little bit of, like, almost like a clicking. Did you hear, like, a little bit there? You can only hear if you're really close, okay? Here's what I've done. I'm now charging this rod right here with a lot of electrons, so much so that if I even bring it, like, near the hairs on my arm, you might even hear it go, like, click a little bit. Here, let me try it one more time. You can actually hear, like, see the hairs on my arm raise up a little bit. What I'm going to do, actually, is I'm going to bring it near this thing that Alexa's holding up. Hold it really high in the air, would you? Okay. So watch this. I'm going to bring it close. Oh, I need the smaller one. Okay, that didn't work as well as I wanted to. That was disappointing. Let's use a smaller one. It kind of worked, but it wasn't as visual as I wanted. Let's try this again. We're going to make this work. It's kind of like a magic trick. Okay, again, hold it up really high. Okay, so I'm going to charge this up. I'm going to give it static electrical charge on it. Here. Did you feel that? Yeah. I just give him a little bit of a zap. Here. Did you feel a little bit of a zap there? Yeah, that's a static zap, okay? I'm going to bring this near this little ball that Alexa's holding up here, and I hope this works better this time with a smaller one. See how it kind of stuck to it a little bit there? There we go. Okay, it's actually made of styrofoam. Now watch this. As I try to bring this thing close, see how I can actually get this thing to move around a little bit? Okay, like, she's not moving anything, right? See how she's just holding it still, hopefully? I'm going to bring this nearby, and I can actually cause this thing. Can you guys see how I can make this, like, move around a little bit here? Ah, Kaylin, say that loud for everybody. What happened? No, you have it right.
No, I'm not used to say it for.
She said, is that because it absorbed the electrons? Here's why. This thing was charged up with electrons, which we noticed because I kind of zapped him with it. As soon as these things touched right here, they both have electrons, and now they're going to repel each other. So as I bring the stick near this thing, see I can make it like move around a little bit? Isn't that kind of cool? Yeah, just like magnets. Now I want to show you one more demo here with stuff that I have. You're going to have to be able to see these little leaves right here. There's two little leaves inside here. So if you can't see them, you're going to have to come to a spot where you can. So kind of gather around here because it's a small scale demo. So here's what I'm going to do. I'm going to take this rod right here. I'm going to charge it up with electrons, and I'm going to zap them again. It's charged. Yeah, it still works. Okay. Now watch what happens when I bring the rod close and I touch this thing right here.
Wow.
Did you guys see how they moved apart? Now, okay, granted, in 2018, you're probably not like, whoa, that's magic. But I'm like 300 years ago, scientists didn't know why this was working because they didn't know about electrons yet. All right, let me do it one more time here. I'm going to charge this up with electrons, and then I'm going to touch this thing right here, and all of a sudden, these two little leaves have moved. Let's talk about why. This had electrons on it, and then I zapped the metal here with more electrons. You know where the electrons went was inside these little pieces of metal, and they're both filled with electrons. What's the charge on electrons? Negative. Well, negative. So if this guy right here is negative, and that guy right there is negative, what do negative things want to do? And that's why they spread out a little bit here. Okay. Let me do this one more time here. I'm going to bring this guy close and touch it. Oh, let's ground it, actually. I'm going to get rid of the electrons. Yeah, as soon as I touched it, I took the electrons out of it. That's a ground wire. So as I bring this guy close again, watch, as I touch, see how it moved there? That is electrons that went from here to there, and they're now in there, splitting them apart. Okay, if you weren't able to see, can we change out? So, can those of you who did see it, can you go sit back down, and those of you who didn't see, come on up here? Because I want you to see this idea. Yeah, thanks. Who didn't get a chance to see this? Okay, come on up here, okay? Come take a look. I want you to see this, guys. Were you guys able to see? Okay. Anybody else not see? I'm going to do this one more time here. Okay, come on up here. So what we've got going on here is there's these two little leaves inside here. Okay. So what I'm going to do is I'm going to take this thing right here and I'm going to charge it up with electrons with static electricity, right? Raj, I'm going to shock you in a second here just to prove it. To give you a little bit of a... Oh, you didn't feel it. No? Did you get a little shock there? Yeah, okay, that's probably all it's going to be though, right? Yeah. It's a little shock. Okay. So this thing is now really full of electrons, really negatively charged. As I bring it close and I touch this thing right here, see how those two little leaves down there at the bottom, they kind of moved? Here, I'll ground it. Right? And then I'll bring it close and I'll touch. See how those little leaves down there just moved all of a sudden? Let's talk about why. There were electrons on this, and the electrons went onto that and through there, and they went into those two little leaves. But if they're both electrons, which are negatively charged, negative things want to repel each other and get far apart. And so that kind of proves the existence of charges, which is kind of cool. Does that make sense? Okay, so go sit back down again here. I'll do some more demos later. So I hope that you guys were able to see the little demo there. Sorry if you weren't. I guess you just chose not to get up, I guess. You still saw. So most of my next slides here are kind of pictures that describe how static electricity works. You guys good? You ready? So let's start talking about this picture right here. Let's say that you have two different pendulums right here, and one's positive and one negative. Well, they would want to push each other away, because like charges repel each other. Or let's say they're both negative, just like that experiment I just did. They would want to push each other away. But we know that things that are positive and negative charge, if you have one of each, they will want to attract each other. Yeah. Now again, is this electricity though? No. It's just static electricity. because for it to be like electrical current, it has to run through like a circuit in a loop for forever. This is just like a one-time kind of like zap. Okay. I've got some more pictures I want to show you here. Guys, can we be focused again and not throw things? Okay. One of the concepts I need you guys to be aware of is called separation of charge. I want to go back and discuss Rutherford's idea of a nucleus. Once Rutherford realized that electrons can be pulled off of a nucleus, it meant that you could separate them. It means that positives and negatives, let me go back to this picture here. Positives and negatives are not stuck inside the same atom, but this negative here, it can move, it can be released, it can be liberated. Okay. And that really matters when we talk about separation of charge, because anybody ever wonder why, when you rub the balloon on your head, why it sticks to the wall? It's due to separation of charge. Let me try to explain it here. Imagine that you had something that was neutral. And one of the best ways that we can illustrate something being neutral is we draw like positives and negatives kind of spread out, where there's kind of an equal number, fellas. You have kind of an equal number of both. You have a positive and a negative, and a positive and negative. But let's say that you bring something really negative close to it. So this is something that is negatively charged. Well, what do negative things want to do near other negative things? They want to go as far away as possible. And so all of the electrons in here all of a sudden move to the far end. And all of the positives stay on this end right here. I want to try one more demo one more time, and hopefully this one will work better one last time. I'll just hold it myself this time. What we're hoping to see here, oh no, they got stuck together. Shoot. Hang on. I should be more careful with this. Sorry, you guys have to bear with me while I untangle this. Shoot. That is not good. Okay, which way do you go? I'm going to have to cut it. There we go. Okay. I need you guys to watch this really closely here. What I'm hoping to show you, and I feel like I need to ask guys, can we make sure you keep our attention here? Because I feel like it's gotten lost a little bit as soon as I kind of let everybody go and move around a bit. I'm going to charge up this rod. What we're hopefully going to see, if this works well, is that this little ball is going to become attracted to this, and then it's going to like touch it and repel. Oh, the string had touched it. Did you guys see how the string touched it there? Move the string to their side here. Let's try this again. We'll get there. This is going to work. It's subtle. You really have to watch carefully. The little ball on the string is actually going to move towards the rod. Did you guys see that? Let's watch it again. Watch it again, just in case you didn't catch that. So, everybody ready? You gotta watch carefully. I want to make sure it's still, and I want to put the string away from it. Do you see how it got towards it and sucked towards it? Like I didn't move it towards it. It got sucked towards there. One more time. It shouldn't actually stick to it. It should touch it and then repel, actually. Okay, last time. Kind of cool. Okay. Okay, so let's talk about what happened here. Okay. You guys ready? Okay. So here's what we just witnessed. We had a negative rod. And what ended up happening is, as soon as that negative rod got close to the little like hanging sphere, what ended up happening was all of the electrons got pushed away, because electrons push other electrons away. So all of the electrons that were right here, they got pushed to the far side of the object. But you know what that ended up making happen? Is that the positives were on one side, the negatives are on the other side. We call that separation of charge. Now, why did it all of a sudden swing towards it and become attracted? Well, what do positives and negatives want to do towards each other? They want to attract, which is why the ball swung towards the negative rod until they touched. And as soon as they touched, now the ball and the rod were both negatively charged, and then it swung away from it. So what actually ended up happening was it swung towards, and then it touched, and it swung away. And those are some terms I need you guys to know. Okay? So here's a slide that talks about charging by friction. Basically what's happening is, if you take that fur and you rub it on the rod there, it becomes more negatively charged. Look at this thing right here. See how there's 1, 2, 3, 4, 5 positives? But now there's 1, 2, 3, 4, 5, 6, 7 negatives. Can we count again? 1, 2, 3, 4, 5 positives. And 1, 2, 3, 4, 5, 6, 7 negatives. There's now more electrons. Okay, so where did the negative come from? When you were rubbing the fur on this little rod right here, it picked up extra electrons. Static electricity. Exactly. Let's talk about why. Why only the electrons? It's back to Rutherford. Where are the protons found? In the nucleus. Protons can't move out of the nucleus. And they're stuck in the nucleus. But where are the electrons? Well, the electrons are now outside. They can move. So here's a slide that talks about the word we need to talk about when it's when things touch each other. The word is called conduction. You probably heard this word at some point before in your life. Imagine you have a sphere that has some charge on it and another one that doesn't. When two objects touch each other, the charge will naturally move and go from one that doesn't have charge to one that does have charge. Just like when I touched that little rod there to the little metal ball there, the charges, they moved. So you can see here that there's charge on this one, there's not here. Well, when they touched each other, it kind of spread out. We call that conduction. That's where you know. Okay. But there's also a concept called charging by induction. And induction is where things don't actually touch, but there's that separation of charge involved. When I charged this thing up right here, again, you might not be able to see this from where you're at, but I'll just do it once here. I'll try to hold it up for everybody. To ground it. When I bring this nearby, can you guys see how those leaves are moving a little bit when I bring it nearby? Okay. That's the charging by induction, where what ends up happening is all of these negatives right here push all of the electrons to the other side, and it causes this split where this is positive and this is negative. And what ends up happening is there's actually a force of attraction here. That's called induction. But things haven't actually touched each other yet. They're just really, really, really close. Okay. I got a few more pictures here I want to describe, and then we need to move on to the electricity. But this is stuff I need you to know. Let's try to walk through this picture. What's going on in picture A? Well, it looks like you have a positively charged rod. How do you make something positively charged? Do you add more positives? You take out the electrons, yeah. So take the electrons out of this, now you have a positively charged rod. Now when you bring it close to the sphere, see how all the electrons came this way and all the positives kind of go the other way? Is that conduction or induction? That is induction, is the word we use. Because it's not actually conducting charge, it's just causing it to separate in halves. That's picture A. Then picture B imagines, well, what if you had a ground wire? What if there was a wire attached to the ground just like we have on our electrical appliances? You know that third wire we talked about? What if there was one of those? And through that wire, let's say that some electrons came back from the ground here. Now all of a sudden I've lost a positive. See how there were 3 positives right here? Now there's only 1 positive. How did we lose a positive? We didn't. We didn't lose a positive. We just, from the ground, picked up 2 more electrons. And what would a positive and a negative do? Well, they'd kind of cancel each other out. What would a positive and a negative do? They'd cancel each other out. So I didn't actually lose positives. I just picked up a few extra negatives. Well, now we can see that this side right here is still negatively charged. Because don't negatives want to be attracted to positives? But now, this positive, there's only 1 of them. Then we cut the ground wire. Well, now what we have left is now there's 3 electrons and 1 proton. But that's not really true. There were actually 3. It's just these guys have an extra electron to kind of cancel them out. And I've now made a negatively charged object. This is called charging by induction. Because did anything actually touch? No, nothing actually touched. Conduction, though, is when 2 objects touch each other and they both get some charge. Here's another picture. Let's try to describe what's going on here. Here we have a negatively charged object. And this guy right here has no charge on it. But like, are there positives and negatives there? Yeah. It's just for every positive, there's a negative. For every negative, there's a positive. For every positive, there's a negative. There's an equal number of both. And if there's an equal number of both, we don't bother writing them because they cancel each other. Well, then imagine that you bring this negative object really, 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 really close. Why are there only positives on this side right here? What happened to the electrons? They went down through the ground wire because the electrons got pushed as far away as they could. Because do electrons like to be by other electrons? No, they repel each other. So the electrons went down the ground wire. Well, then we cut the ground wire. One second. Well, now there were 3 electrons, but those 3 electrons have been pushed down here. Now they're missing. When you cut the ground wire, now you're left with a positively charged object. CBAS. And this one right here, good question. They want to spread out as much as they possibly can, which is why they're not all huddled together in a corner here. So they spread out around the outer surface as much as possible. Anybody ever had the hair on your arms kind of stick up a little bit? What's actually happening there is there's probably electrons, and they're trying to get as far away as they can as possible, and in doing so, they're making the hair on your arms stick on end. Okay? Has anybody ever seen a Van de Graaff generator? We're going to use one in a week. It's the thing, it's like the big sphere, and then you put your hands on top of it, and it causes your hair to go all frizzy. Anyone ever seen one of those before? Okay. We're going to use one of those in a week. It's the same answer to the question I'm giving CBAS here as to where all the electrons go. They don't want to be near each other. All of these electrons right here, they don't want to be stuck together. So they try to spread out as much as they can. So there'd be one here, there'd be one there, there'd be one there, there'd be one there, there'd be one there, and there. And they'd try to get basically as far away from each other as they could. But they have nowhere else to go. They're stuck on this object here. Does that make sense? So, however, these electrons right here, they do have somewhere to go. They can go down this wire, and so they do. So, here's what I need you guys to take away from this last few minutes. The words conduction and induction. What's the difference? Do they touch or not? If things touch each other, it's called conduction. And if things don't touch each other, it's induction. But you can still make things move by induction. The electroscope is the item that I just showed you here. So one more time, let's talk through what's happening. Here, imagine you have a positively charged rod. Again, how do you make a rod positively charged? Do you add more positives? You remove the electrons. Yeah. So say you can take the electrons off of this rod. Well, here's what's going to happen. This device right here, all of the electrons are going to want to become attracted to it. And all of the protons are going to get pushed down here. Well, all of the positives down here, they're going to want to repel each other, which is why the leads separate. But did these two things even have to touch? No. Now, a couple hundred years ago, magicians used to make tricks out of this. They didn't even know the science because it wasn't until 1907 when Rutherford discovered the nucleus that we even knew that electrons and protons could separate. They didn't even know about that yet. Because remember, they thought that the plum pudding model existed, where there was a positive core, and there were negative bits inside of it. So until they got rid of that model of the atom, they didn't even know what was happening. All right, let's move on. Now that I've discussed static electricity, though, it's more useful for us to discuss electrical current, which is like electricity. Okay, actually, no, I do have one more static electricity to discuss. Your mom does your laundry, maybe? Maybe you do. Good for you if you do your laundry. But let's say your parents do your laundry for you, and you put clothes in the dryer. Anybody know what a bounce sheet is? A little sheet of paper you put inside there. What does it do? That's one reason, but actually it's for other things. It prevents cling, static cling. Because here's what happens. When your clothes go through the dryer and they go around in circles, you know how the dryer kind of just runs in a rotating circle? It's very similar to this, where things are rubbing with each other. And as they rub with each other, it creates electrons on here. I can even see all the hairs on this thing standing up. Well, that's what happens to clothes, and they stick together in the dryer due to static cling. That's static electricity. What the bounce sheet is supposed to do is, yes, make it smell nicer, yeah, but it's actually supposed to remove all the electrons so that it doesn't, so your clothes don't stick together. You ever like do your laundry and take the clothes out and you like go, and like there's like a little bit of like you can hear like the ripping apart. That's actually electrons you're hearing. Okay, let's move on now. Now I want to talk about electricity though. Okay, in order for electricity to work, this is no longer a one-time charge or zap. This now requires a circuit. It has to keep going in a full loop. Why do our lights turn off when you turn off the light switch? Well, because you break them. You have like a bit of a gap here. Usually we have a switch of some type that turns things on and off. Right? Almost all electrical devices need a switch, otherwise they'd always be on. Okay. I need you guys to know a couple of terms. Okay. One of the terms is the word load. A load is whatever you're trying to power with electricity. For example, a load could be a light bulb, because its job is to make light. A load could be a fan, because its job is to make mechanical energy by spinning. A load could be a speaker, which is supposed to make sound. A toaster, which is supposed to make heat. It could even be a car, which does a lot of different things. It kind of does a whole bunch of these things at once. But that's what a load is. It's the device that converts electricity to some sort of form of energy. There are then three main parts to any circuit. You have to have a power source, which is like a battery. Something has to provide you the electron flow. You have to have wires. If you don't have wires, where are the electrons going to travel through? And you have to have your load device. It has to do something. Now, there could be other things involved. You could have fuses. What does a fuse do again? And if it does overheat, what happens to the fuse? It melts. Yeah. Is that what you were going to say? And it breaks when it gets too hot. Yeah. Or you could have a switch, which is intentionally going on and off and on and off, right? But like the main three things you have to have are a power source battery, some wires, and a load. So let's talk a bit now about the main point of today's lesson, which is about measuring electricity. Okay. Suppose that we have an electrical circuit going on. Yesterday we talked about safety. We have to be careful around electricity because what can electricity do to humans? Okay, it can shock you, it can electrocute you. More specifically, it affects your muscles. And probably the biggest muscle in your body is your heart. And it can cause some pretty big problems heart damage-wise. So the word we used yesterday was current. I want to try to describe current to you now. As an analogy, I find this works well. Imagine that the kids walking down the hallway here, each of those kids is an electron. And as they walk, that's electricity, right? Because they're moving from one spot to another. Now let's say that 3 kids walk down the hallway. Or let's say that 300 kids walk down the hallway. Well, 300 compared to 3 means you have more current because there's more of it happening. Does that make sense? So current is basically how many electrons can move. And we often have different wires depending on how much current there is. This is a 14 gauge wire. It's a very small wire. How many electrons can fit through this wire? Well, maybe like a few at a time. But if you have like a really big wire, like a 3 gauge wire or a 30 gauge wire, it can handle more amps because it's thicker, if that makes sense. There's more room for the electrons to flow through it. That is what current is. It's how many electrons. Kale, calm down. It's a little bunchy right now. I know. Nice. Okay. So current is basically how many electrons are able to move through a wire. However, there is also resistance. I want to talk about resistance for a bit. Imagine that you guys are walking down this hallway again, and all of the people in the hallway are electrons. But now, rather than it being like right now when classes are in and it's pretty easy to walk down the hallway, imagine that like it's break time and there's a million people all in the hallways trying to move somewhere. And like other people get in your way. You get what I'm saying here? That's resistance. And different wires have different amounts of resistance. Again, the bigger the wire, probably the less resistance there is. And the reason why is that some things are good insulators, others are good at conducting. Now there's a second way of measuring electricity though. It's called voltage. Stay with me, people. Some of you aren't giving me your best focus. I've only been talking for 35 minutes. It's not that long. Voltage is another way of measuring electricity. Let me try to give you another analogy to describe this. Again, imagine kids are walking down the hallway, but some kids are walking and some kids are running. That's voltage. Okay? Current is how many kids or electrons are walking down the hall. Voltage is how fast they are moving. And so if you have someone who's walking down the hall versus running down the hall has more voltage. Does that make sense? Which one was the dangerous one again? Current or voltage? You guys remember? No, it was current. Because you only needed 0.1 amps of current to actually be fatal. Which means that it's about how many electrons go through you as opposed to how fast they go through you. Yes? Okay, so in that analogy, I know it breaks down. But really what's more dangerous, would you rather get run over by one person or 1,000 people? Yeah, okay, so it's the current that matters more, right? Because if we're going to use this analogy, you're getting trampled by them, right? So although voltage does matter, current is more important, okay? So let me take this analogy one more time from the top. Stay with me. Guys, this isn't our best day today. I want better focus. Please. If you're walking down the hall versus running, that's your voltage. Running is high voltage. Walking is low voltage. So if the electrons going through the loop are just taking their time, that could be 5 volts. If the electrons are going, foo, 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 that could be 1,000 volts. Okay. How many electrons you have is your current. If you have 3 electrons versus 3 million electrons, that's your current. And current is actually what's more dangerous. Okay. The words I have on here is voltage is a measure of how much energy the particles have. Basically, the faster they go, the more energy they have. Yeah, that's what I've got on the slide right here. The words I need you guys to know is that current then is measured in A. Current is measured in A. Do you guys remember what A stood for? Amps. Okay. And voltage, this one's a little bit easier. Voltage is measured in V, which is volts. Okay. One is speed, the other one is how many. Let me give you another analogy. I've done this one before. Let's say I'm going to drop some pens here. Let's say that I take one pen and I drop it. Is that high or low current if I take one pen and drop it? But what if I were to take all of the pens and drop them? Okay, but let's change the scenario a bit then. Let's say that I were to drop them this far, or let's say that I were to drop them that far. What have I changed if I only drop them a lower distance? The voltage, because now they weren't going as fast, right? So if you like my analogy, if you drop a whole bunch of pencils from up here, this is high voltage, high current. If I drop one pen, it's high voltage, low current. If I drop them from down here with 5, high current, but low voltage. And if I just drop one of them, low voltage, low current. Okay. And we got to be careful when we work with our voltage and current because they often go hand in hand. And we don't want to have too much because that can cause electrocutions. Okay. Here's one more analogy, and then I'm going to move on to the math because we got to finish that before the end of the day. Imagine you had a water tank. And that water tank sprung a little leak. Let's say it was a little leak. Well, then you'd have a little bit of current. But let's say it was a big hole in the water tank and water was gushing out. Well, that's current because there's a lot of things moving. How does voltage apply? Well, voltage applies to how high above the ground it is. If the water tank has the water fall that far, that's not a lot of voltage. But if it falls like this far, that's a lot of voltage. But what really matters is both how far does it fall, for like how fast it can get to, as well as, well, how big is the hole? Is it leaking one drop at a time? That's not very useful. But if water is just gushing out of there, that's a high amount of current. Okay, we're now ready to get to our math calculations. I promised this was coming. So we need to then take some measurements of both voltage and current. I need you to know the tools we use before we do our math. Anything that measures current is in something called an ammeter, because it measures amps. Anything that measures voltage is called a voltmeter, because it measures volts. And I know this is crazy, but if it has an A on it, it measures amps. If it has a V on it, it measures volts. Wow. Okay. There is a device that measures both, by the way. It's called a multimeter. It looks like this. You might even have one in your house. Your dad might have one in a garage, maybe. A multimeter can actually measure both voltage and current. You just switch the little toggle. Okay, here we go. Here's the math part. This is probably the hardest part of today's lesson. I'm sorry that you kind of had to wait through all the preamble, but this is kind of the main part that I wanted to get to. There is a relationship between current and voltage in a math formula. And I like this picture here. Amps is how much you have. And so in this example right here, this is like a guy trying to fit through like a little bit of a tube. And voltage is what gives it the energy to push it. However, there's one more factor. It's called ohms, O-H-M, and it's the Greek symbol omega. Guys. And it's about resistance. It's what slows things down. Okay. Again, imagine you're in the hallways here, and you're trying to move from class to class, but the hallways are full of other kids. That's the resistance getting in your way. These three factors always go together. The oomph you get from push by voltage, the current, which is how many things can move at once, but it also matters based on your ohms. And this is the formula we're going to use. The formula is R equals V over I. So let's talk about this for a bit here. R is resistance. It is what tries to slow things down. The more resistance you have, by the way, the more friction there is. And the more friction there is, the more likely it is to start on fire. Can I say that one more time? The more resistance you have, the more friction there is slowing it down. And that can be dangerous because that's what starts electrical fires, especially if you still have high current or high voltage. V is your voltage, which is all about your energy. It's what gives you your push. And then I is the letter we use for current. I don't know why we picked the letter I, but I is for current. And it basically is like, how many electrons do you have? Let's try some questions now. Oh, you want to go back here? Sorry. Yeah. Probably not. Because, I mean, it's kind of like when you have to rub sticks together to make a fire. Like, it's possible, but, like, you'd have to, it's going to take a while. It'll be warm. I don't think you're going to make a fire. Kale just does this for, because here's what's going to happen, Kale. It's probably going to rub your skin off before anything else, right? Like, you're going to get a rubbing rash. Right? So, I don't imagine you're actually going to start a fire with your hands. Okay. You guys ready? I got 20 minutes left. I want to make sure I finish this and give you guys some time to work on it. Let's say you have an electric stove hooked up to 240 volts. That's the standard voltage for like a big stove, 240 volts. Let's say the current flowing through the stove is 20 amps. What we would like to know is how much resistance is there. Okay. So I need to do a little bit of a mini math lesson with you guys here. The formula we just wrote down is R equals V over I. Now, in this particular format, it's actually perfectly set up for us. We are looking for the resistance. Stay with me. Okay, I know it's been 44 minutes. I need another 5 or 10. But we know how much voltage we have. Because doesn't it say right here the voltage was 240? So this V number is now going to get replaced by number 240. And I is current, which we know is 20. So all you need a calculator to do is take 240 and divide by 20. 12. But one more thing here. What is the unit for resistance? It's this funny looking omega symbol from the Greek alphabet. And that's 12 ohms of resistance. Okay. All you need to be able to do is divide some numbers by each other or multiply some numbers. But you're probably going to want a calculator because you maybe can't do it in your head. Let's try another example. Oh, I don't have another example. I'm going to make up another example. I think I didn't have enough in my notes here. Let's say that I told you that you had a resistance of 10 ohms. And let's say that I told you that the voltage you were using was 120 volts. By the way, 120 volts is like standard household voltage. Let's say I wanted you to find how much current you have. Here's how you'd go about doing this. The formula was resistance is voltage over current. But here's the problem. Last time I was looking for this resistance number right here, but now I'm not. Now I'm looking for this current right here. So what people often use is they use the triangle method of figuring out how to make this work. Here's how you use the triangle method. You're going to put the R in this corner down here, and then R was equal to voltage over current. So I'm kind of making a triangle out of this where resistance was equal to voltage over current. Here's how the triangle method works then. On this side of the triangle, you are multiplying numbers. And on this side of the triangle, you are dividing numbers. Let's say that you're looking for the resistance. What you do is you cover up resistance, and then you see what's left. Well, what's left is voltage divided by current, which is what we did before. But what are we looking for this time around? We're looking for I. So here's what you do. You cover up the I, and then what's left? Well, there's voltage and resistance. Are they next to each other or on top of each other? So you have to divide. So what we're going to have to do is we're going to have to take our voltage and divide by our resistance. So if I take 120 and divide by 10, it'll give me 12 amps. Let me try a few more examples here. Because is it 120 divided by 10, 12? But then what is the unit for current? Current is measured in amps. Let's try some more. We're going to do a lot of examples now. Let's say that I told you that the voltage was, let's say we didn't know a voltage. Let's say we were looking for that. Let's say the resistance was 2 ohms, and the current was 7 amps. So let's say that's the information I gave you. Here's how you'd solve it. Use the triangle. The formula was resistance equals voltage over current. What do we not know? Okay, so I'm going to take the eraser, I'm going to erase out voltage. What should I do with the R and the I numbers then? They're on the same level as each other. I should multiply them, yeah. So I'm going to take my resistance and my current, and I'm going to multiply 2 by 7 to give 14. But here's the most important part, not just 14, 14 volts. Okay, here's why this is important. When you're doing your math equations, either you're going to end up with a volt, an ohm, or an amp. In my class, especially because I'm the physics teacher here, if you ever write down just a number without a unit next to it, I will not give you full marks. I need you to tell me what unit we're measuring things in. Volts, amps, or ohms. Okay. If you just tell me the answer is 14, 14 what? You need to be more specific than that. Okay. This is the first formula that we're going to learn. There's actually a lot more. This is just the first of many that we're going to learn. Okay. So here's what I need you guys to be able to do now. If I give you information about volts and current and ohms, you should be able to use this triangle right here and solve for whatever is missing. Let me show you your assignment now. Let's talk through some of the questions on your assignment. First question on the assignment. In your own words, can you tell me what energy is? We did that yesterday. Second question. Can you tell me 5 different forms of energy and give me some examples? For example, luminous energy, which we would get from a light bulb. Or mechanical energy, which we would get from a blender. I've also got some questions here that talk about conductors and insulators and electricity, but I wanna fast forward here to this question here, number 12, because I want you guys to start practicing this. If I give you a voltage and a resistance, can you now tell me the current? Or if I give you an amp and a resistance, can you give me a voltage? Or if I give you an amp and a voltage of resistance, okay? You guys should be able to do all the way up to question 12 on your assignment now, okay? Now, I know I'm running out of time today, but I really want to suggest, can you guys start working on this and not procrastinate and leave it for later, because we're going to do 2 assignments this unit. As well as, no projects. No projects this unit. Okay. So, okay. I know you guys are starting to pack up. Does anyone have any questions about our day? Okay, then let me give you a couple passing thoughts, and then you can take off if you like. 1, I'm gonna put a new rule in my class. Although I've normally let you guys kind of leave and go work wherever you want, I'm not gonna let you do that if your name's on my board though, okay? Because I don't like that it's December almost, and I've still got some things that are not finished. So starting on our work day on Friday, if you want to work outside of the classroom, I need you to be caught up to date. Because otherwise I'm gonna want to sit there and work with you and get you caught up, okay? So I will still give you flexibility and freedom, but not if you're behind, okay? 2, if you are behind, I will help, I want to help. Come find me during flex. If you want to redo anything, I will help you redo it, okay? 3, start on this assignment, okay? You can do a good chunk of it. I haven't given you a progress log or a due date yet, but please don't procrastinate. That's the worst idea I can give you. Okay. Any questions? Okay, that's all I got. So if you guys would like to, you're free to take off. We'll see you tomorrow. Oh, one more thought actually. Can you please print off your notes before tomorrow's class? Because I noticed a few of you don't have them. Print them off. It's useful.
I handed in all my progress logs up to now.
Okay, so I just need to catch up then, right?
Yeah.
Okay.
And everything I also sent in the oil transportation project.
Okay. That's probably the email I'm seeing right there, isn't it? Okay. For some reason my computer is glitching now. Why is this thing not